Thank you very much. It's a real pleasure to be here this afternoon. As my former colleague, Professor Khalid, pointed out, my name is Mohammad Shahidehpour, and I'm here this afternoon to talk about a subject that I really love. The photo that you see here is a picture from my office. Actually, I took it with my cell phone. And it shows the Chicago downtown in the background, which is about 2.5 miles from our offices. And the campus is in front of you. So we run about, it's not, of course, University of Maryland. We have a very small university, primarily technical. About 78% of the students are in engineering. And we run about 52 buildings, which we were able to convert that to an island and microgrid, as Professor Khalid pointed out. In a sense, we are able to separate the campus from the larger grid as need be, and run it as an island. So we learned quite a bit in doing that. Much of the work was funded by U.S. Department of Energy, except since we finished the project, now everybody's interested to learn more about what we did. So all of a sudden, we've got a lot of enthusiastic investors and individuals who want to invest on the subject of microgrid. So I always start my slide by a picture of Edison, because he was actually the first engineer who built a microgrid in the United States. So the power system that he established in Lower Manhattan in 1881 was actually a microgrid, in the sense that those days there were no major transmission lines connecting his facility, his operation, to neighboring systems. So he pulled wires from his power plant to local shops and residents, and that's how he started the first microgrid. And interestingly, the microgrid that he set up was a DC system. So we're going back. It looked like he was way ahead of his time. We are building DC microgrids as a way of the future for a number of reasons that I'm going to discuss. But nevertheless, the system that he initiated represented the largest engineering system, man-made, man in the sense of human being, system that National Academy of Engineering identified it as the biggest in the 20th century. So we owe him quite a bit. There are a number of reasons that this subject of microgrid that I'm going to talk about has attracted attentions depending on where you are in the world, or in the United States, which region of the country you're in. But in particular, in the eastern seaboard where you are located, microgrid has attracted a lot of attention, primarily on the subject of reliability. And that sort of started from the recent days of Hurricane Sandy. Decided to use these slides. You can see the footprint of Sandy and the enormity of its impact. Basically covered so many states in the eastern part of the United States, and so many businesses and homes were crippled. The point that hospitals were out of power for 2 weeks and patients had to be relocated is not acceptable. You're living in the United States, and the issue of not having power in a hospital is something that we need to work on. And we're lucky that states and the government are looking into the subject of sort of looking more into distributed generation, distributed control of electric power systems, localizing the sort of reliability, enhancing or improving the resilience of electric power system. Let me point out in the outset that there is a big difference between reliability and resilience. We use those two words intermittently and together, but the point is that reliability relates to low sort of impact, high reliable sort of events. Like every day you can have an outage in your neighborhood. Resilience relates to very low probability of high impact events. So something like this that you see on the screen, it relates to resilience, not reliability of the system. So in a sense, what is a smart grid? Because that's where we started the whole thing. It was an event that started in response to economic reliability, security, environmental mandates that was sort of placed in our system. We need to do something about that. You hear a lot about cleaner environment, lower cost energy, less import to the United States. All of those sort of push this smart grid forward as far as implementation in the United States. The same way that I can, when I was in Professor Kalik's today or last night in the hotel, that I could use my laptop and communicate with the server in my office in Chicago, which because I know the IP address of that device. So I can sort of get hold of server and then do all the work server in Chicago. If you have a sensor that has an IP address, and that sensor is on your electric car or on your dishwasher or whatever appliance you work with at home, then you can remotely turn that device on and off. So that's sort of a beginning of this notion of smart grid, in a sense being able to locally and remotely control devices. So that has two advantages. One is that you can send a real-time price to that device and then turn it on and off when it economically makes sense. But also you can receive signals from that device. So if that device is out of power in a real time immediately, you will know that the device is out of power. So it has both economic advantages and from reliability point of view, you can be, you will know where the sort of a pinpoint is. It is the case where, like, if your neighborhood doesn't have power, utility has to send a truck to see which feeder is out of power and fix that. Now, utility will know in real time, momentarily, which component is out of power because they're receiving data from that smart device. So basically, it's a two-way communication that serves a number of purposes. We're talking about the system that we have, sort of this is going to be sort of focal point of my discussion. We started our microgrid project back in 2006. At that time, there was a gentleman by the name of Bob Galvin who was sort of chairman of Motorola. He was in the latter stage of his business as a career, and then he started thinking about other things other than telecommunication. But he was the one, basically, he's credited, or his company's credited, for building the first cell phone. So he was pointing out at that time that when he designed the first sort of prototype cell phone in the size of a suitcase, so then he took that to Washington and showed that to lawmakers, and they said, oh, we love this. How do we get this? And they say, oh, you got to sort of change the policy. You got to do something with the telecommunication system because there is no room for us to promote these cell phones and wireless systems. So he came to the idea that, in the latter stage of his life, that we need to do something about. He had two pet projects. One was energy. He said we need to do something about that. Apparently in 2003, when we had a major blackout in the United States, New York, he and his wife were having dinner in lower Manhattan or somewhere in Manhattan, and then everything turned dark. So he said, no, we can't do that. We got to fix this system. And then the other one that he had was transportation. Pet project that he had was transportation. And he said, why do we have congestion? Why do we have to have traffic jams in our country? Why can't we fix that problem? So on this energy side, he put together a team. We met in O'Hare. That was in 2006. There were like 20 of us. And he invited people and paid them big dollar to come to that meeting. And then his point was, guys, tell me what we can do about our energy infrastructure. Why can't we fix that? Then at that time, he was such a visionary. He started talking about distributed generation, microgrids. Nobody really was talking about microgrid at the time. And so at the end of the meeting, we said, okay, why don't you sort of do that project at IIT? I mean, if whatever you have, because he was closely related to the university. He was the chairman of the board earlier. So he gave us some money and we started. At that time, we had no idea what DOE was going to do and all that stuff. So we did this study on the university. We sort of had an idea what we were going to do. In 2007, U.S. Department of Energy came up with this sort of a call for proposal. And then we submitted that. We got the funding. We got the largest funding in 2008 to start that. So as you see, this map of the country shows areas or entities that are funded. As you see, it covers areas from Hawaii all the way to the eastern part of the United States. So we are in that corner in Chicago, and we got the funding to do that. At that time, the point was to reduce the peak. It wasn't really a microgrid at the time. So these were sort of what you see here. These are the mandates that we introduced. We're going to reduce our peak energy consumption by 50%, reducing our base power by 20%, demonstrating the value of perfect power. The reason we called it perfect power was because of the book that Bob Galvin wrote at the time, and because he was funding our project. We said, okay, we call it perfect power. And the point was that university load was going up, so we were going to build one more microgrid at the substation at the university. We already had two, So we're going to build the third one. So we started talking with the university, and we said, instead of building the third substation, why don't you give us the money? From this project, we can lower our consumption to the point that the third substation will not be needed. For those of you who are not so familiar with the power system, substation is sort of a gateway that you have for importing power. So at your university, University of Maryland, there are a number of substations that connect the university to the larger grid. And that's where you get power into the university. So we had two of those where we used to get the power to the university, and they were already loaded to the point that the university was going to build the third one. And we said, instead of building the third one, why don't you give us some money to manage the load, bring it to the point that the two would be sufficient. So university gave us $5–6 million. We got funding from the Department of Energy. So all in all, we had close to maybe $10–15 million to work with the industry support. Then we started building this microgrid at the time. So that item that says sort of deferral of the plant substations refers to the subject that I just told you. And then reducing the sort of outage cost and savings is a major issue for us at the time, and I'm sure is a major issue for you here, to the point that we used to spend, even at the small universities we have, about $500,000 a year on managing outages. So I'm glad to report that now we're done with the project. We just finished. The Department of Energy visited us, and then we just delivered the project. We're finished. I'm glad to report that since we set up this microgrid, outage time has been 0. We have had no downtime at the university because of this microgrid. So that by itself, that you can build a system anywhere in the United States, 2.5 miles away from downtown of a third largest city in the country, to the point that the lights will always stay on, shows, no matter how much it costs, microgrid is the way of the future. It's like the ad from a credit card company that says, price of this and price of that, price of convenience, it's basically priceless. It's the same thing with this. When it comes to keeping the lights on, when it relates to security or critical load, whether it's a hospital, the police station, or whatever, you cannot put any price on that. You have to fix it. And that's what we did here. So I'm going to show you how we did that. So the next item is the new products. We as a university, like you, we do research. So the work that our faculty and students did was commercialized. The number of companies which started based on the work. And all of that comes into the name of smart cities. We work with Microsoft and a bunch of other companies. So smart city is sort of a buzzword right now. Everybody wants smart cities, smart in any sense. Keep the cities, from, whether it's a resilience, whether it's economics, whether it's reliability, make the city smart. So you can basically replicate this idea that we developed here in a smart city, because university like yours is a city. You've got dormitories, you've got faculty offices, you've got a hospital. You are a city. So if you can build a microgrid here, then you can replicate that in any other place. So this is, again, sort of a model of the sort of an aerial view of the microgrid. This is from the bottom going all the way north. Highway, this is the major I-94 on the western side. Eastern side gets closer to the lake. North is closer to the, approaching the downtown Chicago, and we are at the tail end of the campus. Sort of pointer. Anyway, this building here is a little small to see that, but that's our gymnasium in the corner. And this is where we're building a DC microgrid. So that building is going to be standalone, but this entire building is going to be DC. I'll show you. So the map that you see on the right-hand side is the sort of a view of the campus, in the red, shows where the campus is located. This is sort of a model of the entire campus. As I said, we've got about 52 buildings. And what we've done is that we have converted the campus into 7 loops. So these color ones show the number of loops on campus. So here, this is like loop number 1, loop number 2, loop number 3, all the way down. I'm in this building, so I'm in loop number 7. And these loops, each loop is connected either to our north substation. So these are the 2 substations that we have, the generating plant. And these small sort of white circles that you see, these are smart switches. These are 3-phase, 4160-volt switches. This is one of them. These are buried at 3-phase. these switches communicate with each other using fiber optics, and they do self-healing in about 6 cycles. So in 1/10 of a second, the system will identify the location of the fault, opens and closes the switches, system is back into normal operation, something that was completely unheard of. I remember, I've been at IIT almost 32 years. I remember the days that we had outages for hours, for days. And you can imagine how detrimental that is to the research that the faculty does. So this is sort of a model of this is a campus with the 2 north and south substations. These 2 are the utilities substation that shows for the techies how power is transmitted to the university from the grid side. So when we have any kind of island, we just basically open these ties. So we disconnect these power from here, and then the campus will be an island. So these are a series of phasor measurement units. For those of you who are interested, phasor measurement unit is a component that basically measures, it's like a meter except it uses a GPS. So you can synchronize phasor measurement units so that the entire measurement is taken at one moment of time. The problem, for instance, we have in the eastern part of the United States is that there's a meter in PJM in Pennsylvania area, there's one in your area, there's one in Chicago, and then when these measurements are taken by these meters, there's a time difference. So when you just send them all to one center for processing, by the time they get to the center, the time has changed to the point that they're not synchronized. So by using these phasor measurement units, you can also add the element of time so that you know when these measurements are taken. And then PMUs are getting more and more popular. Thank you very much. Yeah, these PMUs are getting more and more popular, not so much at the microgrid level because distances are shorter. But here we are using them because this project was funded by Koreans. They wanted to test new technology, so one South Korean company came to us, wanted to install this, they paid for everything, so we have them. So we have about 12, 13 of these at different locations where we sort of collect data. So they provide about 60 measurements per cycle. So not only do we have our traditional meters, we also have the PMU, big data, then we play with them, which is fun for students. So this is that entire model of the campus. So this is the grid coming in. This is the PCC where connects us to the grid. And then these are the 2 substations, and the entire campus is at 4160 volts. So at 4,000 volts, we operate the campus. And then, we have, as I said, we divided the campus into 7 loops, all the way to loop number 7. So each loop is sort of self-sufficient. So there are major buildings connected to each loop. These 3 sort of blue color boxes represents those 3-phase switches that I showed you earlier. And each loop individually can be opened and closed, connected to either south substation and north, and the 2 substations are connected through a normally open switch. So if there is a problem with one of the substations, the other substation can feed power to whatever was being connected to the previous substation. So we've got a total of 9 megawatt of generation. It's 8 megawatt of combined cycle natural gas unit. Also, we have a 1 megawatt of renewable energy at the university. We've got about half a megawatt of battery. It's a flow battery that we charge at night when the price of energy is negative, and discharge it during the day. So we make money on the arbitrage. On that side of it, the battery is here. We're about to install another 1 megawatt of battery. So battery is big. Talking with the professor at lunch, that battery is going to be big. And as you see, we got solar PV everywhere. Different buildings at the roof have solar. Now, of course, question is, why do you need solar in Chicago? It's always cold and it's always rainy and snow. But the interesting part is that we have lots of solar when we need it, because when the real price of energy is really high is in summer. In summer, we have as much sun as we want. And that's when we really need solar. Of course, we use it throughout the year, but in particular in summer is where these things come into picture. But we also have a wind unit on campus that it rotates if you ever spins. If you're ever in Chicago, please stop by and we'll show you. So it's really an engineering system. When I went to school, like you ladies and gentlemen, some 35, 36 years ago, I only learned about KCL and KVL and electrons. I never learned about managing a project and litigations and unions. But now I do that as well as other things. So it shows, how versatile you have to be, at this stage and you know, how many things you may end up doing after graduation. So this is our 8 megawatt natural gas unit. As I said, it's a combined cycle natural gas. It's got 2 jet engines, each one generating, it's a Rolls-Royce engine, it's generating about 4 megawatts. And we use that all the time for generating electricity on campus. So this is again the view of one of the buildings, which shows the rooftop solar. You see our wind unit in the background here, and then the rest of it is downtown. This is our flow battery on the campus. And we also have a solar canopy that feeds the charging stations. So all the utility cars at the university are electric. So these cars get charged at night, and then during the day they just run all over the campus. So thanks to the Department of Energy, everything is free as far as running these cars. And then also faculty, if they have cars, they just park here and get free charge. We don't charge anybody for using this. Now this canopy is of course connected to the rest of the campus. So if it's this cloudy day, the charges for these electric charging stations will come from the rest of the campus. And on a sunny day, this provides energy. And also this is our sort of latest architectural, this is a solar tree. This is my building. So we are installing this in front of the building. You know, when you talk about rooftop solar, ordinary people have a very difficult time relating to that because it's always on the roof of the building. Nobody goes on the roof to see the solar panel. So unless you are in Arizona or somewhere in California, you really cannot see the solar panel because, you know, areas like yours where it's so congested, they always put the solar on the roof of something. Whereas here, we decided to actually design and install this so that the passerbys, you know, people who are driving on the street can actually see this. So this generates about 3 kilowatts. It's not big, but then it's wired to a cafeteria that's inside the building on the first floor of our building. So people who are eating in the cafeteria now get free charge for the solar, for their phones and iPhones and laptops and all that. So it's a really interesting venture. We're just installing it. We'll be completing it this year. So this is another toy that we have on campus. So the entire system, the control on the campus is done at 3 levels. We do a control for the entire campus. So we have one master controller that does the control for the entire campus. The second level control, so we apply our hierarchical control. So the second level control is the building level. So all the buildings at the university do have a Siemens controller. The master controller for the campus, we designed it, and all the engineering jargons, and they had scheduling and locational marginal prices and mixed integer programming and all that went into it. Then the second level is the building level, and all the components within the building are connected to that building controller. And the third level control is a device control, lightings in the room and all that. So about 30% of our load is shiftable. So we shift loads that are non-essential, non-critical to off-peak hours, and then that's how we save money. We save university about $1 million total. You can imagine if small university like ours can save $1 million a year, and the university is generous enough to give part of it back to us for operations. So a university like yours can save quite a bit. And that's only on the economic side of it. So then we apply these group controls, you know, primary, secondary. So when we do the controls, you know, then these are for like power electronic devices, so we manage the entire campus. So this is the control, as I pointed out. This is the master controller. Master controller is where I am, in my building. And then from there, we control the entire campus. Now, there is no operator for this system, so there's nobody sitting there controlling the system. Again, what I'm showing you, what I'm discussing today, what I'm explaining this, is sort of how we do it. Otherwise, if I get into derivations and equations and all that, there are about 50 PhD students who work on this project at any given time. We'll get into all of that, but I know that may not be of interest right now. So if you're interested to see how we did it mathematically, you're more than welcome to look at some of our work and publications. But master controller is where all the signals go in. And then, as I said, the second level is the building level, and the third level is sub-building. Use a lot of Zigbee, Eaton, whatever device we have. So these master controllers send signals and receive signals. So if there's a major outage at any time in the Chicago area, it does send signal to all those switches that you saw earlier and disconnects the campus from the larger grid. Then we are islanded. Then once we are islanded, then we have to manage the frequency, the voltage, all the electrical components. And it gets to be an interesting venture. In a sense, if you don't know what you're doing, the system can collapse right away. You have to know exactly how to manage the system from an electrical point of view in order to keep the voltages and frequency within permissible range. So this device collects all the signals from PMUs, from meters, building controllers, and sends the signals. So we do basically do a day-ahead scheduling. For those of you who are familiar, grid operators in the United States for a larger grid, like where you are now in PJM, they do a day-ahead scheduling. And what it means is that they schedule today for tomorrow what they're going to do. They look at the forecast for load, forecast for energy, solar, wind, whatever is out there. And then based on that, they figure out how much they need to generate for tomorrow. Because larger generators, you don't want to keep them on because you have to pay for fuel. If you turn it off, then you may not have time to turn it on, because if it's a steam unit, you have to generate, warm up the water and generate steam, and that could take several hours, if not days. So they do day-ahead scheduling, if not longer. But let's say day-ahead scheduling, where they schedule for next day how much load there's going to be, and then based on that, they figure out how many units they need. So if in your area the load is going to be X gigawatts, then they figure out how many generators are more economical to turn on for tomorrow. Then they do hourly, and then based on that, they turn the units on, and then they do real-time scheduling for when tomorrow comes, because there could be some discrepancies. If all of a sudden there is an event, people may turn on their TVs, or if it's a cloudy day, people may turn on their lights. So the load could increase all of a sudden. Then they do second level of scheduling, which is in real time. So we do the same thing here. For this system, we do day-ahead scheduling. So today, we are scheduling for tomorrow. We do the forecast for the solar to see how much solar energy we're going to have, because we will have the solar energy at our access only if sun is shining tomorrow. So we need to figure out how much sun is going to be tomorrow, so how much solar are we going to have. Then we look at the wind to see how much wind is going to be available, so how much power we can generate using our wind unit. Then we look at how much load we're going to have. Okay, weekend loads are going to be much smaller. If all of a sudden tomorrow is going to be an exam day, the load is going to go up. So load will vary. Like summertime, people turn on their air conditioning, load will change. So load will change on a daily basis. So you do forecast for the tomorrow's load, and based on that, we turn on our units. So this fellow here, the master controller, does all of that. And then based on that, it turns these generators on and off. And then if there's a major event, as I said, sends a signal here to disconnect the system. So there's no operator. Everything is done automatically. Except if something is broken, since we have built a SCADA system for this system using OSI Pi, then I get SMS, I get text messages, or system starts blinking. Let me know what's wrong, and we go and fix that. So this is the model of our SCADA. This is sort of a campus. It's hard to see it here. But all these wires, these are different switches, different buildings. This is the entire system. This is one of the rooftop solar. So if something goes wrong, the system starts blinking. This is based on the OSI Soft Pi system that we have developed. Really interesting technology developed by OSI Soft company that we use that. And then we can zoom on that, look at individual like switches, behavior of the system. So we collect a ton of data, and we play with that. We do planning for like a year in advance, how much fuel we want to buy, issues related to cybersecurity. We do a lot of studies based on the data that we collect. So as far as the resilience is concerned, as I pointed out, if there is a major outage at the university, we do islanding. So that's how we keep the system in operation. So if you ever have, let's say, a major earthquake, luckily we never have that. We'll never have that. But if there's a major, weather-related or whatever other reasons event in Chicago, then we'll be able to island the campus. Now, what we do is that we have identified, we are able, as part of our operation, to put, from a control point of view, campus into 6 different modes of operation, mode 1 through 6. And mode 1 means, very critical loads, like our hospital or our data center or the office of the president, whatever that is. So those are the critical loads. Then the second level would be like less critical loads, and the third level would be less than, goes all the way to level 6. So if all of a sudden, right now, at this moment, we need to create an island on the campus, we identify how much load we have, and then we put the campus into one of those 6 modes of operation in order to keep the lights on. And then after that, we do the reconnection when the system is back into normal, and then we operate the system. Now, the interesting part is that all of that, you know, this issue with the islanding and everything else that I pointed out, we follow the standards that's set by IEEE. So everything is done professionally in the sense that we follow the steps. It's not like, you know, okay, let's see what do we do now today. Everything is followed based on the rules and regulations and standards of the industry in order to manage the system, because we're connected to a larger grid. So if there is no major outage, which we haven't had in Chicago, luckily, then we go through this drill about 5, 6 times a year. And what it means is that we assume there is a major outage, and then we create an island. So that could be a very hot summer day, a very cold winter night. We actually disconnect the campus and see what will happen. And then whether or not we are able to manage voltages, frequency, keep the lights on, keep the dormitories on, and everything else. And we usually do it at hours where life is impossible, to make sure that we're ready for the worst. So at the normal day like today, we may be generating all the energy that we need because our power plants are running, and we have enough solar, and the wind unit is turning. However, we remain connected. At any given time, we remain connected to a larger grid. We just reduce how much we are importing. So that import could be 0 right now, but we're still connected. So the switch is closed. But if there is a major outage, then we open the switch. So there's a sort of a distinction there. So there's just some boilerplate information. This is from our final report to Department of Energy. There's a lot of numbers here. I just listed this for people who are interested to read. But the most exciting part is this, that this microgrid and the renewables and all of that we have introduced compared to the days that we didn't have, we are about 6.5% better off as far as environmental concern. So we can demonstrate that this microgrid can actually save life in the sense that we clean the environment. But these are actual numbers. Vetted and approved by the U.S. Department of Energy, we're about 6.5% better than what we were before. As far as cost of the unit, as I said, we spent about 13.5, about $14 million on this project, where about $10 million of that was actually building the microgrid, and another $4 million was on the R&D part of it. So the money that we gave to our faculty and to our students and all of that, the R&D part of it was about $4 million, and the actual hardware was around $10 million. And this shows where we spend the money, actually. One of the things was that, as I said, that one critical, the pinnacle of this project was deferring the cost of substations. So this project saved about $7 million savings. $5 million the cost of that additional substation at the university that we didn't have to add anymore. And then $2 million that utility didn't have to do it on their side because we reduced the load. So $5 million from IIT side and $2 million on the utility side, a total of $7 million, this $13.6 million investment from the Department of Energy and others brought in. So here, in addition to $1 million a year, so it's all saving. It's a great idea. You guys should do the same. And then, as I said, this shows that we're saving about, again, I'm putting a lot of words here for those of you who want to read later, but the bottom line is that this, in the operations side, this unit is all saving $1 million a year for the whole university. So the net present value of this is around $300 per kilowatt. So now, what we're doing now, we are actually exporting our ideas in different ways. One is that we are interconnecting microgrids. So we say, okay, we have one. Why don't we find somebody else who wants to have one? Then we can talk. We can play together. So we have a microgrid at the university that excited our utility in Chicago area to build one. We have about 12 megawatt load. They have about 10 megawatt load at that region. So a total of 22 megawatt, there are going to be 2 microgrids. The 10 megawatt is going to be paid by our utility. There's going to be an actual physical tie between the two. So we just received funding from the Department of Energy to build a master controller for these two microgrids talking to each other. So there are a number of reasons that microgrids should be interconnected. Now, what does that mean? It means that like you can have a microgrid here at University of Maryland. There could be another microgrid at the Army lab and another microgrid. And these microgrids are sort of autonomous operation. They're doing their own thing individually and every day. You at university manage your own load. However, if there is ever a major outage in this area, then there would be another level of control where these sort of a master system will talk with these local controls in order for these microgrids to share resources, because the critical load at University of Maryland could be less than your day-to-day operation. Only maybe, as I said, your data center and your hospital and maybe your dormitories. There are a few places that you want to keep the lights on. The remaining part could go to the Army lab. And if they have extra, they can give it to you, or they can supply a hospital and keep the entire neighborhood on. So there is a benefit of sort of clustering these areas and also interconnecting them. Basically, the microgrid in a nutshell, I started talking about that, but that's what it means is that you put a fence around all these distributed generations. See, right now you go to many parts of the country, in Arizona, California, Florida, everybody wants renewable energy. People are putting that stuff on the roof of the houses and buildings. There is no way for the grid operator at the higher level to manage that, because I don't know what I'm doing in my house. So if you put a fence around my neighborhood in the sense of a system, electrical system, and call that the microgrid, and there's a master controller or controller for that fenced area, then we can manage our load within that neighborhood, which is fenced, and then collectively can talk to the grid operator. So the essence of microgrid is to be able to manage loads that are otherwise impossible to control for the grid system. So in this case, the loads at each microgrid are supported individually, and then in case of major outage, they're supported by the interconnected system. So interconnecting microgrids reduces the complexity in the control and operation, as I alluded, and then this way these DERs, distributed energy resources, are managed in a very cohesive way. So this is the essence of a community or interconnected microgrid. So for instance, this could be ours and this could be like a utility company, and there is a sort of a centralized control. So we do our own thing, they do their own thing, and then we are connected through this system that manages us. Now the interesting part is that some of these, for instance, one of the microgrids could be completely DC. The rest of them could be all AC. So how this master controller, that's the subject of this project that we are doing for the Department of Energy, is to interconnect these guys and then manage the system, mostly from a reliability and resilience point of view, but also it could encompass the economics. So this is a model that we have. Again, this is a university one that I showed you earlier, and then this is the one that's going to be built by the utility. And there's going to be a physical tie between these two. Now, this one that the utility is going to build has some very critical loads. The Chicago Metropolitan Police Headquarters is there. There's a major hospital. There's a major ballpark. So there's some very critical loads here. That's why the utility is very interested in building this blue microgrid. And then here we are. So we have our own resource that we can share with them. Although I was talking with the professor that they're planning to build some fuel cell and then install rooftop solar and all that. But the most exciting part of it is that we'll be sharing loads, as I have alluded here. So these are our partners for that community microgrid. ComEd was the prime, but we get money. We work with Alstom, Microsoft, OSIsoft, Quanta, Schneider, SNC, you name it. Cisco is part of the game, and then some others have joined us. So big project that we're very proud of. The other issue that we are doing for this microgrid is to build a DC microgrid. Now, much of the discussions and much of the load that you have here, these are AC loads. So power is generated by your plant or imported from the grid, and then you down level to 110 volts or whatever it is, depending on the size of the load, and you're using that. However, the whole country is shifting toward direct current, DC. There are a number of advantages for DC. The primary reason is these guys. So the rooftop solar or PV is the DC generation. So if I have an AC load, then I have to go from DC to AC. I have to do conversion. So I generate some heat, and then I have to pay for that hardware. If I have a data center, for instance, the data center, all the computers, all the laptops, all these computers are DC. So then you're going to go from the roof that is DC to AC and then back to DC in order to supply your computers. So why don't we just connect these two? Let the DC go to DC. The other one is that the trend is to convert a lot of these lighting to LED. LED is going to be a big issue. Major cities throughout the country are looking into converting the high pressure sodium lights, these orangey color lights that you see on the streets, to LED. LED has a number of advantages. One is that the LED lights are, for those of you who are familiar, it's very efficient, extremely more efficient. The second one, the good thing about the LED is that it's dimmable because it's DC. So you can actually dim the light. So if right now it's quite binary. If you look at the streets, the lights are either on or off. So let's say they turn them on at 6 p.m. 6 p.m. the sun could still be out, but then you still see the lights on. In fact, when we drive through the city of Chicago streets in daytime, bright daylight, you see a bunch of street lights are on because the sensors are broken or the person in charge doesn't know that they're on. With this system, if you put like the street lights as LEDs, then you will be able to remotely, centrally control them. So not only will you know which one is broken, the same two-way communication that I pointed out earlier, you can also control them. So as sun is setting, you can turn them on. And you can, since they're dimmable, you can change the intensity all the way to the maximum when it's completely dark. It has a number of security advantages. If there is a sort of a neighborhood that needs the police immediate attention, then the lights could be much brighter than the rest of the city, or it can start blinking, or do fancy things basically, or if people are passing by, the lights could turn on and very, very bright. And if there is nobody, there is no pedestrians, and the lights could be dim. They estimate the number that we did in the city of Chicago, which it has about 450,000 lights. We saved the city easily $2 million a year by converting the LEDs, lights to LED. And those high pressure sodiums are old anyways. They need to be replaced. So this is a good thing. So, and then we can extend that, talking about this subject. The next project in that respect would be traffic lights. Again, the traffic lights, you could manage them centrally using the same technology, using LEDs, and traffic lights, you could locally control them in the neighborhood to the point that if the traffic is in one direction, then you can change the lights to the point that you sort of reduce the impact of the traffic. So it's just the beginning. There's so much going on. But this DC, basically, this is with converting one of our buildings to DC. Again, we just received the funding to do that. This is actually our gymnasium. Keating Hall is our gymnasium. And the reason we are targeting our gymnasium is because about 80% of the lighting is, 80% of the load is lighting. Lots of basketball courts and all that. So they have high bays with lots and lots of lights. So then what we are doing is that we are creating two buses from electrical point of view, two nodes. One is a DC bus, the other one is an AC bus. So then we already have about 300 kilowatts of rooftop solar in that building. So one set of arrays are going to be connected to the DC bus, the other set is going to be connected to the AC bus. So here we only need a DC-DC converter. And ask Professor Khalid how to do that, if there's any questions. And then all the DC loads will be connected to DC bus. And also there is a bidirectional converter. In case we don't have that much load here, we can send them to AC. And then this building is connected to the rest of the grid on campus. So this building by itself, which as I said, we just received the funding, so we're going to finish it by end of December. It's going to be an islanded building because we're going to put the storage, a battery in it. So this battery will be charged during the day. when we don't have enough load here, and then runs the load at night. So the entire building is going to be self-sufficient, net zero operation, all because of this solar. So sky is the limit. We also have, as part of our project, this is downtown Beijing. This is a central train station in Beijing, China. So we have all the numbers. We're converting this one to a net zero project. And the reason, basically, it's going to be a microgrid. And the reason we do that is these trains are electric. All the trains being operated in this area are electric. So basically, you can do energy harvesting, where one train that's entering the station, all that energy is being wasted right now. On the electric trains, the way they stop the train is that they put all that energy into a resistor, basically wasted. Like in Chicago, all the street trains or CTA are electric. So there's a big resistor that basically, when the train is slowing down, all that energy, the inertia, goes into the battery, go to the storage and gets wasted. And the city of Chicago, the train system is broke. They don't have money. And yet they're wasting all that energy. So this project that we are doing is these trains, as they're coming in, all that energy, basically the motor will be reversed by changing the field current to reversing that, converting it to a generator, push that energy back into the building. So as one train is coming in, it pushes the other train out. So all that energy that originally was coming from the station, now one train feeds the other train. And the surplus, the difference, will be saved at the train for lighting purposes. So all the numbers that we did and we presented to them shows that this building will be a complete microgrid with no rooftop solar or any of that. All we are doing is to use the energy that's coming from these trains. We just had a paper recently in the Electrification magazine that explains how we're doing this. So let me talk a little bit about how this microgrid fits into the larger system. How much time do I have, Professor? 10 minutes, okay. So let me just very quickly how this sort of is embedded, because microgrid that you build is part of a larger utility grid. So how would that fit into the system? So basically, these microgrids can support expansion of systems. So if in your area the plan is to build more electrical facilities, T&D, the question is, do we build another large generator, or do we build a microgrid? Basically, do we localize the generation by putting storage and batteries and fuel cells, or do we go and build another 2,000 megawatt nuclear unit or 1,500 megawatt coal unit? So here we're just showing that no, the solution should be to build distributed control and use a lot of storage and distributed energy resources. So the way they are solving this problem is sort of a two-stage problem. And we do the master planning here, and this of course includes sort of operation. So we use a lot of decomposition techniques, and then here we do the reliability, whether the system can keep the lights on. And if there is a large expected energy not served, then we go back and then change the original solution, and then we sort of do back and forth between the two stages until we're happy. Now this planning here, the master planning, could include microgrid. So here we are looking into various transmission distribution options, and then at the reliability stage, we are looking at, let's say, 1 year or multi-year indices that exist for reliability studies, and then if that number turns out to be smaller than what we expect, in a sense, if there's a chance that the system could face some outages, then we go back and change the solution. So this is a sort of a mathematical representation of that. As I said, problem is solved. These are, GENCO stands for generating companies, TRANSCO stands for transmission company, and DISCO is distribution company. So these are the unbundled components of electric power system. So up here, these three components will bid into the system. And then the system will do basically, these components from a planning point of view express their ideas and their vision and mission and interest for expanding the system. So that goes into the grid operators, the system that does the co-optimization of generation, transmission, and microgrids, check the short-term solution, because the short-term and the long-term would have to be coordinated. for feasibility reasons, and then from that we do the optimality to make sure that cost is minimized. So we keep doing this mathematical solutions. If this solution is all fine and dandy, then we take this optimal plan, we check the reliability, and then if it's not satisfied, we continue this. So this is sort of a, from an optimization point of view, the procedure that we follow in order to do that. And this component here, it has a microgrid. So basically here we are saying, is it better to build another transmission line in the eastern seaboard to feed power to University of Maryland, or is it better to make University of Maryland to be a microgrid? So basically this is the objective function that has the cost of generation, cost of transmission, cost of microgrid, and cost of unserved energy. And cost of unserved energy means at some point it could be more, could be cheaper to pay some customers to turn the lights off. So instead of building another plant or turning on another plant, if there is a factory that can work at night or some other time, instead of peak hour, why don't we just give them some money so that they shift their loads, pay their workers who are going to work at night, and then keep that factory off during the day. So this would be the cost of unserved energy, basically the money that you spend in order to reduce the impact of this. So from an optimization point of view for planning, we have these sort of 4 components. And then each one I've explained here, like generation has the investment cost, salvage value when you're selling it, operation costs and all of that. I don't want to get into all of these. And then so we do a master planning, which is basically, originally it's the integer problem, but then once you go into a number of iterations, it turns into mixed integer. And then there are constraints including all the microgrids and then the components for the individual system that you're going to add, and we do the reliability. So as I said, once you're done with the master planning, then we do in the subproblem, you do a reliability check, where you, in the reliability check, you make sure that you keep the expected energy not served at the minimum. And then if the expected energy not served is beyond the limit, then you go back and solve the problem again. So a very simple example to show how this microgrid fits into the larger system. Given a very simple 3-bus system, now all of a sudden we are adding one more bus, or let's say University of Maryland is using more energy. So the question is, do we connect another line from somewhere else to the university? Do we build a power plant nearby to feed power? Which one of these two? I'm not talking about microgrid at this stage yet. These are from the utilities point of view. Which one of these options, or maybe both, you have to consider in order to supply the additional load here. So here I'm giving the information. If you add this generator, it's about $4 million cost. These are low numbers. If you build a transmission line, it's about $5 million cost. And then as you see, the load is going up. So the load of the system is going up, and the question is, how do we solve the problem here? So we solve the problem using that same method, and then the solution comes back and says, the better option is to build this transmission line rather than adding a generator here. So this is the details of how we solve the problem. So we solve the problem. This is, since it's a very small system, we were able to get the solution in 2 iterations, and it shows the convergence and the planning cost. So we're done. So the final solution, it says, build this transmission line, forget about that generator, and that solves this, or feeds this additional load here. Next example, we said, okay, let's add a microgrid here. So this is another example. The load here is increasing. L2 is increasing. So the options are, put the generator here. So all these dotted sort of options show the options for planning. So you can build a generator here and build a transmission line to get to this L2. You can build another generator here, and this line is strong enough to supply that. Or build a microgrid here. So consider different cases. Base case planning, just a generation. The second one is generation and transmission planning. The third one is generation transmission planning with the microgrid. So only generation as an option. The second one is generation transmission, and the third one is a microgrid. So these are the details. And then this is the final solution, basically. So this is the case where we have only generation, generation transmission, and the microgrid. And as you see, the microgrid solution turns out to be the cheapest of the 3. Of course, these costs, $32 million. These are cheap because the system is only 3 bus. But in any case, you see about 10% reduction in the planning cost when you use the microgrid. Now, of course, here I'm showing you all the details for the ones who want to read later as to how we did that. But anyway, for this specific example, microgrid is a better solution. And the reason it's better solution, because we don't have any issues with the outages, because here we are solving, we are applying like the stochastic solution, so all the Monte Carlo options for outages of transmission lines of the generators. By the fact that you're localizing the generation, you are reducing the dependence on the generators and transmission lines that are feeding power from the remote location. And locally, you can also manage that. The same way that I said for the university, that we identify our loads and manage our load. Here, by localizing the microgrid, you can manage the system correspondingly. So here we did another system, a little larger system, 118 nodes, 118 buses. And this is sort of a solution where we consider only generation transmission, and with the microgrid. And then again, that you see the microgrid turns out to be in billions of dollars. Much better solution. Again, I'm providing these slides for you to take a look at it later. See. One interesting project, as part of this planning that we did, this is the map of the country with all the grid. So here the color shows existing transmission lines. Like this green are the 765, which is the highest voltage in the United States. Red is the 345, which is the lower voltage. Then it is yellow, then it's blue. So different types of voltage. As you see, we are heavily dependent on at least this part of the country. Import from the Canada. On this side of the country, we import a lot of hydro, again from the Canada. A lot of thermal generation in the central part of the country, in Chicago. We got huge nuclear units in the Chicago area. And then we feed the power. Now we said, okay, if the load in Chicago is increasing, what do we do? This is before we talk about microgrid. From the generation, basically large grid solution. We said, okay, there is lots of energy, wind energy available in the central plain, basically in South Dakota, North Dakota, all the way to western Texas. Can we take some of that power and bring it to Chicago? Basically build additional transmission line between Chicago and somewhere in Dakota in order to transmit this free power or cheap power generated here, which is a sort of a wind here. But the problem is you can see how congested this is. There's no way to build more transmission lines. Right away is such a critical issue in the United States. Nobody wants to see those big transmission lines in the back of their houses. So it is a problem. And the other one is that when you build a transmission line going from, let's say, Dakotas to, let's say, Chicago, which is the edge of the PJM, you're going to cross all these states. And all those states saying, okay, we want our share. If you're going to cross our state, we need a piece of that pie. Of course, the builders don't want to give them anything to those guys because the price is a premium in PJM, edge of PJM, which is Chicago. So they don't want to give it to them. So basically, those states don't agree with building transmission lines. So we said, okay, why don't we do this? Why don't we look into offshore wind? So this is a project we just finished using the method that I just explained. So this is a project that is going to be, this AWC project. It's going to be built in your area to some extent. This is off of sort of New Jersey area. This is the eastern part of the United States. As you see, you have a very small band that you work with because this is deep water. It costs a lot more to build offshore wind. So these little blue dots are about 7,000 megawatts of offshore wind. You can imagine that amounts to maybe about 2,000 poles, 2,000 structures. You can imagine how crowded it is. And then the critical part was that you couldn't close these openings for shipping purposes. So we did the design here, and then for comparison, I'm showing you this, that as you see here, this red shows very expensive prices. This is before the wind is built. It shows how congestion is making your energy to be so expensive. And then the problem with the congestion is that if there is a major outage, these electrons have nowhere to go. It's like the highway, that when the highway is crowded at 5 p.m. in the afternoon, the emergency vehicles, police, ambulances, they have a much more difficult time to get through. So after you build this offshore wind, as you see, all this red turns into blue and green and all that, which is a much cheaper price. So it shows the impact of building these 7,000 megawatts off of this area. So again, this goes to the planning area that I talked about. Of course, this has not the microgrid, but you can also localize this based on the microgrid. let me skip this. Two other things I want to say and then I'll finish. Professor Khalik brought it up. We started a new center called C-SMART. It stands for Center for Smart Grid Application Research and Technology. And the first project of this that is funded by Microsoft and alike is to build these street lights that I pointed out. The essence of this center is cybersecurity. See, this is one of the streets in the university. This is the new LED light, and this is the old clunky sodium light. And you can see the difference. And this is only 10%. You can imagine how much money you'll be saving if you spread this all over the city. And then this is the technology, how we do that. So you take the measurement, and we use a Silver Spring network, send it to our control center, so we manage all these lights. These are the new LEDs. The problem with this technology is that these radios are wireless. So then somebody can hack them. So you can, if you install this at the university, as we did, then somebody can hack all these lights and turn the lights off at night when people are walking by. Or if it's in the city of Chicago, you can turn the entire city off. So Microsoft and Silver Spring, and in particular the city of Chicago, paid for this project. And we are doing some studies to see what are the ways of reducing this. So this C-SMART, the first project, which is the streets, but the essence of it is this cybersecurity. So we've got big projects coming through this C-SMART. So now that we've finished with the microgrid project, we're sort of expanding our horizon, and this is one of them. I just came back from Virgin Islands, where we're building first microgrid, and there they're charging people in Virgin Islands $5 a month per person for managing streetlights, because the streetlights are old, and the streetlights are high-pressure sodium like this, and they cost more to operate. And we said, okay, guys, we have an idea, so we'll see how that goes. So this is the REACH project that also Professor brought it up. REACH stands for Renewable Energy Application to Conserve Humanity. So now we are going all over the humanity. So we had this is our project that we had in Virgin Islands. This is Virgin Island. I go there a lot. It's a really fabulous place to work. The downside is that their price of energy is 53 cents a kilowatt hour. You know, here you pay 10 cents, and people complain. Imagine they pay 53 cents in Virgin Islands. And in Virgin Island, those territories, basically islands in that part of the world, turn out to be very impoverished. They don't have any money to begin with. And now they're paying 53 cents for energy. So we said, we have an idea. Why don't we just build a microgrid? So this is a project. This is funded by U.S. Department of Agriculture. We never had, we had funding from Department of Defense, Department of Energy, Homeland Security, never from agriculture. So now all of a sudden, Department of Agriculture is interested in microgrids off-grid for locations where they don't have any energy. So we got this, and then this is where we were signing the agreement to do that, and then we're going to build this. I'm done.
So let's open the floor for a few questions. Yes, please.
So you mentioned IAT's microgrid is 12 megawatts, and then you discussed in one of your case studies 120 megawatt microgrid. Is there a general range over which microgrids are optimal?
We figured that anything over 10 or 12 megawatt is not really microgrid, because it gets to be so big that it gets to be like a power system. Basically, this notion of real-time control gets to be much more cumbersome when you go beyond that. So anything over 12, I question that.
The state of Maryland's offshore wind project right now is at 200 megawatts and go up to 1.2 gigawatts. How do you see the impact on the entire energy distribution?
It's going to be significant, Professor. It's going to be PJM. The prices at PJM are relatively high because it's fossil fuel based. So utilizing some of those options. Now, a lot of those are going to be PPA. So basically, they're going to pay for it, and the ratepayers will reimburse them. But in a long term, because you don't pay for energy, fuel, then I think it's going to be very interesting. the entire eastern seaboard is very congested, but the ocean is open. Now, of course, probably Kennedy doesn't want it in his backyard, Lake Kennedy and all that. But I think wind units, the wind energy is going to have a bright future. I think using that is going to be significant. I have the numbers. We are not at the position we can advertise those. But when we did the study for the company that is going to install the 7 gigawatts, it is a clear indication that it's going to be an affordable project that we as a country should look into it. When we talk about saving energy and using less of fuel and all of that, we should consider that we should consider the socio-economic aspect of that. We as a country would have to consider that importing that fuel is very expensive from a social point of view. So the more we sort of get to be self-sufficient, of course, the price of gas is dropping, but how long that stays, I don't know. But utilizing renewable energy and what's available to us in that respect, I think one way of, saving the country for the next generation. Sure. The gentleman, the question he's asking is, okay, if you build a microgrid, then the grid is still there, larger grid, and then somebody has to pay for that and pay for the microgrid. The point here is that utilities in the United States and elsewhere do spend millions of dollars per year, if not more, to manage the system for peak hours. Like in Chicago, the amount is staggering, how much they spend just to be able to keep the lights on or keep the system running for about 450 hours in a very hot summer day, when we really have peak. So if somehow you can eliminate that, you can save utility a lot of money. So building these microgrids, not only do they have socio-economic advantages for the customers when you have hurricane and all that, it can save utility as well. One thing that is critical based on your question, and that is, we are right now, the question that you're asking is because you're putting microgrid into old system of utilities. I think our policymakers in Washington need to look into the entire electricity infrastructure, grid infrastructure, to the point that laws have to be changed, to the point that there's a new business model for the utilities that as you increase distributed generation, as you increase the local control, utilities can make money and stay on. But yes, if you build a microgrid in the old system, ratepayers were taking care of that, now you also have microgrid, it's not going to work. Although from a social point of view, it's going to work. But economically, yes, utilities are going to lose money. So we need to look at it from a different system, the same way that we did it for cell phones. When AT&T went away, when cell phones came around, and AT&T came back as a different company, very different from the original company. The same thing would have to happen to the utilities, that we need to revisit. I personally, I've spent 35 years of my life working with large utilities. I think, personally, I believe that the days of 2,000 megawatt large coal unit or large nuclear unit is going to be numbered. I think we're going to still use the grid. We're still going to use base power. But rooftop solar, distributed generation, smart grid, time of use pricing, they're coming. So we need to look at the entire hierarchy and infrastructure as a new business paradigm. We cannot leave it as is. Very good question. The thing is that, like, let me start by answering your question, explaining how we manage our load at the university. When we have the microgrid, we manage our load. See, when I'm sitting in that control room tomorrow, I know every node of the university because I work with that. So if something goes wrong tomorrow, I know where to cut power. I know which components are working. I know which building is important. I know where I can cut power. And I can keep the lights on based on what is left after that major storm or major. Right now, the way when Hurricane Sandy hit, the entire system was at the mercy of the utility. They had to decide how this feeder was going to be powered, and this feeder could have 10,000 homes connected to that. So they didn't know anything about individual homes. But if you build a microgrid, and that microgrid, let's say, includes 500 homes or 2,000 homes, then whoever is in charge of it or however that's managed, they can identify what is working after the major outage, and then how you can manage the load. So it could be a large generator like what we have. We also have smaller generators in every building. And as I pointed out, in the case of a utility operation, then there's a police station. So you want to keep the police station, turn everything else off. We can localize the problem as opposed to something that is managed by the larger utility. Yes, it could be the case that everything is wiped out and help that. It says, when you design an aircraft, yes, you look into reliability and issues with that. But if there's a major event and the entire aircraft is gone, what can you do about that?
We have two more questions.
Sure. Well, it is sort of moving in that direction. I mean, you see there are houses in California, in the western part of the country, where they are sort of, they participate in net metering and feed power back to the grid. Yes, you can do that. We don't recommend it. I mean, you can do that. Problem is, individual household owners don't want to be bothered with that, and individual household owners don't know how to do that. Unless you are a business savvy or electrical engineering jockey, you don't know how to control these things. So yes, we can move in that direction, and certainly people are allowed to do that and can do that. But I think localizing the control would be a much better way of doing that. Now, we can also, I talked about 3 levels of hierarchy for control, where you have master building and sub-building. You can also go another level below that. You can divide it as many levels as you want from a theoretical point of view. But at some point, economically may not make sense, and from a control point of view, it could be an overkill.
One last question.
Yeah, my question is related to the previous question. So you have given us a very informative overview on the way to utilize the distributed generations as well as for the resilience. There's also a matter of the economies of scale. And to address a little bit, I wonder from the power generation, the microgrids point of view, how do you see the balance between this taking advantage of the scales versus the advantages of the local distributed generation?
Yeah, very good. The microgrids that are built in California and microgrids that are built in your area have completely different objectives. The ones in California are mostly for economic reasons. Lots of sun, electricity is expensive, I have a big lot, why don't I put some rooftop solar, why don't I put some solar in my backyard, and I can reduce my cost. Here you have a different reason. Here it's more like, okay, we're going to have another hurricane coming. What do we do? So when you look at that, at some point you have to put the same way that I saw the problem when I look at the cost of unserved energy, you have to put some value, social value on that issue. What is the price for you to keep the lights on in a hospital? What is the cost of that? What is the price for keeping somebody alive when that person is under surgery and all of a sudden all the lights are gone? So when you look at those things, you can put some value, and you see that microgrids make a lot of sense. But there could be some reasons that microgrid may not make sense. But every study that we have done points out to the fact that localizing control, identifying critical loads, keeping those on, getting rid of non-critical loads, allowing customer participation to play a major role is going to be the way of the future.
So thank you. Wanger, and let's thank our speakers.